Alrighty, well firstly, thank you for being here everyone. Leanne in the back. We are Berber Water, and we're taking part in the WEF student design competition this year for the City of Boulder wastewater treatment plant. And I'm Jay Blackburn, project manager. This is Molly, she's our water treatment specialist. Camilla is our bioremediation specialist, and Ryan is our CAD and chemical treatment specialist. So firstly, I'd like to just go through and lay down an outline of what our proposal covers today. Firstly, we'll go into the problem assessment, move into the current treatment scheme, and then talk about some feasible solutions, new and old school, and how they might fit into our proposal. Then I'll turn it over to Molly, who will do quality control and assurance, and Camilla will finish with decision matrix and deliverables. So what is the problem that we face here at the Boulder Wastewater Treatment Plant? The region, which we all love here in Boulder, is beautiful territory, but it has a natural arsenic concentration when it gets the Boulder Wastewater Treatment Plant of 0.53 to 0.73 micrograms per liter. You can see that the plant does treat about 36% of this arsenic, but we're still left with an effluent way up, like an order of magnitude above the standard of 0.023. You can see that the national drinking water standard is at least an order of magnitude above that, so Camilla will address the bioaccumulation factors that go into these standards. And here's the current treatment path. I'll try not to lose anyone, but we start here with the raw influent, which goes into 3 primary settling tanks. Some of the sludge is drummed from the bottom into the digester, which I'll come back to, but the rest is going to the aeration basin, into some secondary settling tanks, and then it moves along here to the new UV treatment facility. They're trying to phase out chlorine as a disinfectant, and then additionally we have additional biosludge removal, which goes to the digester. Oh, okay, sorry. And we have 4 available structures, actually 5, that can be used. There we go. Sorry about that. Okay, these are additional or available sites where we could use space to renovate. And then we're pretty excited about some of the treatment methods we're incorporating here, and we'd like to use a combination of them, however possible, to do the best job at removing the arsenic.
Okay, so there's a wide variety of processes we can use to remove the arsenic. The question is which one is going to be best for this treatment plant? The chemical makeup is really going to determine what we want to use, what method we want to use. Things like sulfates and nitrates are going to mess up the ion exchange process, so that will make it so we can't use that, possibly. And other things like fluoride could decrease the possibility of absorption processes working. Another thing we need to think about is that there's 2 forms of arsenic mainly in our wastewater treatment stream. There's arsenic 3, also called arsenite, which is a neutral compound, and there's arsenate, which is a charged molecule. The arsenate is actually going to be removed much easier than the arsenite because it's charged, and so basically we want to implement a oxidation process before we use removal technologies. Some of the chemicals that we can use for this are chlorine and also permanganate. They're trying to stop using chlorine because it is dangerous, so we'd recommend using permanganate to oxidate the chemicals, or the arsenic. One of the processes that we are looking at is ion exchange. Ion exchange basically takes a salt-brine combination, and you run the arsenic water through the brine, and it removes the arsenic through a ion exchange process. This is pH independent, but things like nitrate and sulfate are going to be selected over arsenic, so if those things are in the water, then we might have a problem using this. Also, waste brine could also be negative in terms of it can be really hard to send off to dispose of. Another thing that we're looking at is enhanced coagulation and filtration. Coagulation by itself will normally not get us to the point of 0.023 micrograms per liter. So what we want to do is do a mixture of coagulation and filtration by using aluminum base, iron base, and different polymers to coagulate the material. Iron-based is going to actually be the most effective in removing the arsenic, and so basically, also it would work really well because right now they have a problem with iron fouling the UV system, which they use to clean the water later on. Basically, when you mix it all together and then you use the filter, it filters out both the iron and the arsenic together. Yeah.
So absorption. Absorption is a simple one-step process that could be easily implemented into the Boulder 75th Street wastewater facility. You just will implement multiple pack beds like you see in this picture to allow at least 12.5 million gallons per day to percolate through the system in order to reach the level of 0.023 micrograms per liter. They can be implemented into the existing infrastructure, like the empty tanks that are already existing, to be used as the beds. So the main thing that we're looking at for the absorption is the actual sorbents. There are two criteria that we've been looking at to rule out the hundreds of tested sorbents that have been used for arsenic removal. Number one is the ability to attract the arsenic and remove it at these levels. So we need to be able to get it down, and it needs to work at the right pH and the right temperature of the water. Number two is the cost. We need to make sure we have a low enough cost sorbent because it's going to be expensive to get it down to these levels that we need. So we've divided the possible sorbents into two categories of commercially produced and low-cost sorbents. Here are just some examples, but there are benefits to each category of adsorbents. The commercially produced are more well-researched and more easily implementable by the wastewater treatment facility because there's more research and larger testing. Low cost is obviously less expensive and you can reuse byproducts of different systems.
Hi, my name is Camilla Restrepo, and I'm the bioremediation expert. Bioremediation is important to Burger Water because it's sustainable and because it's less energy intensive than most other technologies that are already implemented. And so I've split this up into three sections: biosorption, bioaccumulation, and oxidation of arsenic-3 to arsenic-5 using bacteria. Biosorption is the usage of biomass for passive immobilization of heavy metals. Bioaccumulation is the sequestration of heavy metals through metabolic processes in organisms. And then the oxidation of arsenic-3 to arsenic-5, as Ryan said, is important because arsenic-5 is more removable than arsenic-3. And if we're able to do this with bacteria, this is better because using chemicals is more expensive and more dangerous. The key to making biosorption work is using biomass from the local area. Possible biomasses from around Boulder are waste from the Celestial Seasonings factory, but beer mash from the breweries around locally, and then also right in the Boulder wastewater treatment facility we saw that there were cattail growing in one of the old settlers that isn't being used right now. There are studies showing that cattail does take up arsenic, and this is because the roots in the rhizosphere contain a lot of a lot of iron. And so this would be great if we could implement cattail because it can take up to 50 times the surrounding concentration. Beer mash would be great to use because the Boulder wastewater treatment facility is already wanting to use this to feed their activated solids process. As you guys know, bioaccumulation is a big problem, and through the research at CU, you might know that it's associated with mercury and with bad health effects. And bioaccumulation is also the reason why our requirement is so low. It's 0.023 micrograms per liter, and this is because it's a combination between the drinking water standards and the fish standards, which brings it way down to that 0.023 number. Bioaccumulation can also accumulate other contaminants such as phosphorus, which is important because the Boulder Wastewater Treatment Facility is looking at further regulations being more strict with phosphorus. And so our ideas were possibly mushrooms, and there are certain mushrooms that can bring down bring down the concentrations of arsenic up to 12 22 times, and you can take the fruit heads of the mushrooms and you can put them with the biosolids, because the biosolid regulations are still not strict, not too strict, that you can leave it at a Class B, which is what the Boulder Wastewater Treatment Facility has right now, biosolid standard. And then our pre-treatment AS3 to AS5 bacteria process would use bacteria such as bacillus and other bacteria, and what they do is they have the AS3 contact them, and because it's so toxic, they want to move it to a less toxic state. AS3 is more toxic than AS5, and so they oxidize it using their metabolic processes to the AS5 to be able to survive in their community. And now Jay will talk about how we could implement these bioremediation processes in wetland mitigation.
All right, thanks, Camilla. A lot of you are probably wondering how this would work at such a large scale, with wastewater treatment being about 12.5 million gallons a day. We found another plant in question here that could be used to uptake arsenic. It has been shown by Vanderbilt in 2006 to uptake 1,500 parts per million of cadmium, which is not too dissimilar from arsenic. And to put that in perspective, 1,500 parts per million by weight is 1.5 milligrams per dry weight gram. So that's almost, it's pretty high magnitude. This is what we envision. It might look something like a big field dedicated to maxing out the area possible and growing a combination of plants if possible. Some pros to this method are that it's cost effective, natural, it's aesthetically pleasing, and it requires minimal maintenance, and as Camilla said, we could possibly grow an organic carbon source just outside the wastewater treatment plant. This could improve the efficiency of the activated aeration basin, and some cons, though, are that it's untested on large scale. We might need additional biosolid regulations to be put in, and there's some land and area restrictions that we might come across.
So here at Berber Water, we want to make sure that the optimal design is met by both us, by us. So we do this through peer review and self-review first to make sure everything is perfect. And we establish a line of communication first through Jay to communicate with both Leanne and Cole at the WEF treatment and Boulder Wastewater Treatment. This is the budget we've set forth for the individual tasks. First, we have the alternatives assessment, the design development, and the preliminary design. This total comes to be around $22,000.
So to decide which alternative is most cost effective, we'll use this decision matrix, which uses our criteria that are weighted and our alternatives. We also have a control over here to be able to compare with all our other alternatives. Our top criteria are approximate cost, predictive average drop of arsenic out of the water, and then usage of available space within the wastewater treatment facility. And then our deliverables are outlined here. These are the most important dates for our project, and at Berber Water we want to implement organization and quality, so to be able to come up with the best result. And now I will be pleased to take any questions or comments.
Anything from anyone?
Yeah.
I had a question. To start with, Leanne, or do you want us to?
I have lots of, I have written comments, maybe we can chat afterwards, so I don't take up too much time.
Maybe ask what one of you.
Sure. Well, one question I had then about, I guess it was the absorption. Does that also include a chemical treatment?
Before, if you need to oxidize the arsenic to attract it to the absorbent, then we'll put in the necessary oxidant.
So do you feel like everything except for the wetlands is going to have some type of chemical pre-treatment step?
I would say so.
Yeah, I'd say that's a big
So that both
question.
the arsenic 3 and the arsenic 5 could be removed to the full extent.
And do you have any preliminary estimates on how much land may be required for your wetland?
At least on the order of a square mile or more.
But we were thinking of possibly using these two that aren't used right now. The two flying saucer-like bins.
So I had a question. So you showed earlier the schematic of the current treatment process, which is activated sludge and so forth. Where do you envision this is inserted? Is it way at the beginning, way at the end, somewhere in the middle?
We envisioned it after most of the treatment before the UV, for most of them, or maybe after the UV, depending on what we decided on with the new UV system.
Right, because what complicates it is that if we throw in a chemical treatment option when we're adding a lot of iron and stuff, we don't want that before the UV because we've seen that it lowers the efficiency of the UV and it can also create harmful byproducts by passing it through that intensive light. Carl?
A lot of the treatment processes you suggested are used in drinking water treatment to remove arsenic, but you're applying it to wastewater. Did you see any challenges with the wastewater matrix compared to like a drinking water matrix?
Right. I think specifically the sorption or adsorption has been used to treat infected groundwater and stuff at a really low scale, and it's proven effective. But what we have yet to see is how we can implement that with a relatively low cost at this high scale.
With the other metals and stuff in the wastewater could be a challenge.
And this is why we'd like to implement it after most of the processes, because then we'll get a lot of solids out of the way.
All right. Well, that seems to be it. Thanks for having us.